Okay, so now we are officially recording.
Yes, so thank you to Ahmed for the invite. You know, I got to hear from you. He heard from me from my YouTube channel. And then he contacted me to give this presentation today. So thank you for the opportunity and to get to know you guys a bit there in North Dakota. And the topic that I thought to present today was something that I have worked with in the last maybe now it's going to be 8 years, something like that. So it has been a bit on and off with some like we have worked a bit and done some progress, and then we have left it for some time, and then we come back and do some progress. So it's not, we haven't been continuously working on this, but at least I think it's good to give you like an overview of what we have done. So it's I'm from NTNU, it's the Norwegian University of Science and Technology. We are in Trondheim in Norway, like in the middle of Norway. And I'm presenting is a production optimization can have a lot of meanings, can have, can be improving the production, the maintenance schedule, taking decisions on replacement. But here we're talking is model-based production optimization. And the focus is oil fields with ESP boosted wells. This is the outline. I'm going to give just an introduction, what is done in a general way, and what things you should be aware of in all the steps. And then I'm going to talk about the case we have worked the most, which is on land networks. And there a short comment on bottom hole pressure and the inflow, the effect of the inflow. Then development, which was considerable speed up of the optimization and the way we do the modeling, developing of a proxy model. And then evaluating the effect of model uncertainty, which is is important in all cases, but in this case in particular, because this is a very tough situation to model. And the models, we are going to be poor, or they can be, not have a good accuracy, especially when you when you use it outside of the range of, where you tune it or where you are operating. And then I'm going to present very quickly, I see if I have time, I hope so, to talk about some cases for offshore fields where almost exactly the same method, but of course with other considerations have been used. And then also some final comments. Also, this is not, I didn't do this by myself, but it's a big team behind, and as has been done in some period of time, there are many people involved that have been in the project and then out. So you have people from NTNU. We work with this company in Colombia called Pacific Exploration and Production, and I think they are called now Frontera Energy. A university at Venezuela, Simon Bolivar University, and also the team that from PetroStreams. So just general about model-based production optimization, what do we mean by that? So we have a production system that can be an existing asset that is in operations, or it can be also something that we are planning to develop. And we create a model. And usually, well, we take data from that system. If we have a lot of data, a lot of measured data, we can tune properly and try to develop a proper model. But sometimes we just have a very rough model. Like if we are in the planning phase, we don't have yet much information to populate this model. And I put this arrow going back here because we were in the process of building this model and creating this model. Well, you can do, give a lot of things back to the system. Like for example, sometimes, and it's expected that you will have a mismatch between the model and the actual system. But some cases, the mismatch tells you something might be wrong in your production system. So you might have an issue that you didn't consider. Like for example, you might have maybe something happen in the formation that is producing less than expected, or something is happening in the tubing. You might have so this process, I just put this small arrow here because by creating the model and then computing, well, you will see some discrepancy, you will see some difference, but actually you can actually try to improve the system by doing that process, by creating your model. So then we go to optimization. After you have a model that you trust more or less, then you take it to an optimization, and essentially you have there an engine which runs the model several times to find out something, okay? To either you command it to do something, to either to find more production, to find more revenue, to maybe reduce cost. And there are two ways, so you can do it like in a separate way, like in the optimization engine is moving or is operating the model, or you can also put them very tight together such that the optimizer is kind of almost combined with the model. And then you typically have some optimization engineer that is in the field or is in the office, and you have also a group of people taking decisions that they interact with this optimization framework. And you also have operational constraints. These typically come from the field, or they can come from also from the office. And I put an arrow here because sometimes you include a long list of constraints that you think the optimizer has to fulfill, but actually there are many of these constraints that they don't matter that much. So that's typically you come with a long list of constraints that you should take into account, but you realize that, well, maybe some of these constraints first, where do they come from? If they have some very strong background, they have a very strong reasoning behind them, or also sometimes maybe they are important, but they are not relevant at all for your problem. So that's also something we have to take into account. And from there, we take operational actions if the asset is operating, or we also take some design decisions. So for our case, it's we're looking into fields. This is typically heavy oil. You're talking maybe 12 API, 14 API, high viscosity, something maybe above 50 centipoise, maybe 300. These are operated with electric submersible pumps. Here you have to the left, like a typical layout. Okay, you have the pump, you have the motor, you have a lot of other things. And typically what you can change in these systems is the frequency, or essentially the rotational speed of the impeller. You have a system, this is for a land system where you have a variable speed drive receiving electricity either from the grid, or you can have some diesel generator, for example. You have a remote terminal unit where you can specify what frequency you want to use, and then that goes and regulates the rotational speed of the pump. And also the other element that we looked into is also ESPs, that they have diluent injection. You see here you have your ESP and you have a line in which you're injecting diluent. And the main intention is that the reservoir oil is typically high viscosity, is creating a lot of friction pressure losses in the pump and also in the pipe. And so then what you do to make it easier and to reduce the delta P that you have in the system, then you inject some light, typically some light crude that we call diluent, or also is called dilutant. Okay, and then you end up with a light oil that is kind of easy to handle because the viscosity is much less, and also might be even more attractive to sell it because you can sell it at a higher price. So this is something like similar what you have in gas lift, that here this depicts is the oil rate that you get from the reservoir, from the formation, and then you have here how much you're injecting, and this graph is made at the constant wellhead pressure and a constant ESP frequency. So you see, if you start increasing the diluent, actually you get some increase, and be aware this is some increase, but it's not, you're not going to, well, you're probably going to become a millionaire from this increase, but it's very modest compared to other things. And then after that, when you pass some point, well, actually the diluent doesn't help that much, because you're adding more liquid, and then you're increasing the friction and losses because you're carrying more liquid in the system. So in this case, the optimal is located in a diluent fraction of 12% approximately. And the diluent fraction is how much diluent you're injecting divided by the sum of these two rates. So just, these fractions may be something between 5% all the way to 40%. This kind of are typical fractions. And this is the plot you get. And the performance is like the diluent performance curve. And the increases, they can be more, but usually they are quite modest. Another thing we have that is important to take into account is that we are not pumping always just oil, but you are pumping water, because typically you have either an underlying aquifer which is very strong, or you have a very active water injection. So then for this depicts is the viscosity of the mixture of oil and water. And this typically exhibits, if you have a dispersion, this typically exhibits this behavior, which you have like a point or a water fraction in which you have high viscosity. And to the left, well, you reach the oil viscosity, and to the right, you reach the water viscosity. But you have a peak usually, and here is a bit exaggerated, but you have a peak and a transition where supposedly you have, between oil continuous and water continuous. So really this diluent effect is important, well, when you are below this phase inversion point. Okay, when you are above, it becomes water, and the water is the carrying phase, so then it has less impact, the effect of diluent. So going back to our optimization scheme, we can say a few things here. So for our particular case with ESP wells, we say, well, the models that we're looking typically are, well, from the formation, from the sand phase all the way to the processing facilities. And that typically includes wells and network, the gathering network. Reservoir, I put a question mark because it's used, but it's often not completely coupled with the well and the network. It's simply you take some values from the reservoir model and then you use them as inlet conditions to the well and the network. Okay, and we are going to see one example of that later. Typically, commercial software, we can use also our custom-made programs, not very common, and this model has a lot of uncertainties, and even though it might be a very calibrated model, in the optimization, we are using it to look into other ranges of operation, other operational conditions. And so we have to make sure that even though it might predict very well for the current conditions, it might not be very good for other conditions that the optimizer is going to find. And here, typically we say, well, we set up a problem in which we want to maximize oil production or profit, or you might also want to minimize cost or power consumption. For this, typically you use some software for integrated asset modeling. Can be commercial. You can also use some optimization software to be able to find solutions faster and to be able to have more trust on your solutions. Or you can also use custom-made program, which it could be an issue because it might not be sustainable. If you want to use the same solution in time, you might not be very sustainable. So typical operational constraints, we have, for example, the power capacity you have. If you have generator, if you're using from the power grid, the suction pressure. Also, for example, you don't want to have vapor liberation from the oil. The diluent availability, the diluent costs money, and you typically have some storage of diluent that you don't want to use more than what you need. The specs of the oil, if you want to reach certain viscosity or certain degree that you can sell it at a better price. The processing in terms of typically is the water that you can handle. Also, if you, for example, the crude is very viscous, you might have some issues with emulsion, with separation, with delayed residence time in the separator. And other thing could be the ESP map, how they operate. So here is a chart showing the typical ESP performance. You see here a relationship between the head, which is the delta P divided by density times G, and the rate. So you see typically it follows this curve if you are at a fixed frequency, but then you can vary this frequency from, in this case, 30 to 60. So then you cover this whole range. But besides that, you have also some operational, and here is like by this minimum frequency maximum and this maximum, this blue line and this red line. And this typically is because if you go too much to the right, you're going to have poor hydraulic efficiency, and you go too much to the left, it's also going to have too poor hydraulic efficiency. Or if you have floating impellers in which they are able to stroke actually up and down, you might also have too much wear that they cause kind of early pump failure. Okay, so you have typically looks like that. It's like this trapezoidal shape. And if you have different viscosity, then of course this is going to change. Okay, we're going to see that later. Then what do we do with this model, with this optimization? Well, we want to get, for example, set frequencies. How do we set frequencies in the different pumps? Or how much diluent we inject in each pump? When, for example, maybe the ESP is not good anymore for that application, so we need to change it, or we need to go to a different model. We need to change the number of stages, for example. This could be some of the things. Some challenges. Here you see a plot in time of, this is of the field we were working with in Colombia. Oil production is this, these hollow white dots that is reduced dramatically in time. And then the water cut, which is here to the right, you see how it's increasing and changing very quickly. So you see within the first 200 days, not even a year, you have an increase from maybe 30%, 20%, all the way to 90 something percent. So you have a very, very abrupt change in increasing water. You have this issue of the water and oil mixtures. If you have a dispersion, you have this. Sometimes it's very difficult to predict the pressure drop accurately for oil and water mixture, especially when you have the effect of the diluent and the viscous oil. It might be very challenging. And also there's the ESP, again, the ESP performance curve, okay, for a fixed frequency, and you see the effect that it has to increase the viscosity. Okay, you see that the performance is significantly reduced. So first is, I'm going to try to take you through time. What have we done in time? And first, so the first thing with any optimization problem is to say, well, is it really worthwhile to optimize? Maybe there is a better way that I can define all of these factors without optimizing, because going into the journey of the optimization is like quite, it takes a lot of work, and also you have to involve a lot of people, and then it takes a lot of effort for people to use it. Okay, so you have to be sure that, there is value in that. So this is a case, a simplified case that I showed in this publication, which shows this network. Okay, you have two wells that are ESP boosted, and what you want to know is, well, you want to, by running the model with different input, here we're running with different frequencies, then we run the model, and then we get the results. Okay, the total oil rate, water rate, suction pressure of the two pumps, and then the power. And then we repeat for another point and repeat. So this is just like a brute force approach. And this is useful if you have very few variables. In this case, we have only two. And then I can inspect these solutions. I can see how they look like. So this plot is here shown on the right, and it's showing on the x-axis this is the result of that process. So on the x-axis is showing the frequency of the well 1, change from 30 to 60, and the frequency of well 2 change from 30 to 60 also. And the color code, I should have used I have two versions, but I used the black and white. But you see, this shows the amount of oil that is produced, the total oil production. And you see that, well, one well has much more effect than the other, and because this one has low water cut. Okay. And also one thing you see here, these areas which are shaded, they tell you, well, when one well doesn't flow, the other well doesn't flow, that are unacceptable operational conditions. And here is where I exceed some rating I have on the maximum wellhead pressure. Okay, so you see the area, if you deduct these parts, you're going to have just a reduced area. Moreover, if you go to the pump map, okay, these are that you have to be within this blue and red line that I showed before. Well, then you have, if you want to be within that range, you have a reduction even further of your operational region. Yeah, at the end, the region you have is something like that. And well, you find that the maximum is actually here. And for this system, you might say, well, that's not much. Okay, it's maybe 550. You have here maybe 600, so might be like 10 or 20 standard cubic meter per day. But actually, if you do that for a system where you have 40 wells, then actually 10 by 10, you get a kind of a significant increase. Okay, but the first point is that you get here a strange number. Okay, you get like 47, which is not something you say will drive things to the maximum. That's not going to work in this case. Then this is a study we have done in a project we have done in the Rubiales field. And this was in, before 2015, because this was published in 2015, where we actually applied this method on their system. Okay, and this is the field in Colombia. Here you see where it's located. You see these are the processing facilities. This is the reservoir, how it looks like. You know, it has a very big and very strong aquifer, and actually it's a hydrodynamic aquifer. They don't need to have water injection because it replenishes, the water is replenished by migration. And also it's very viscous. I think it's like 300, 700 centipoise in reservoir conditions. You can have, this is very typical that you have coning from the aquifer. And this is typically how it is produced. You have a lot of these trunk lines, and these trunk lines might have, as I mentioned, maybe 20 to maybe 60 wells. And you have from the template flows to a main trunk line, and then the trunk line goes and collect all the production from the field. And this field is producing, I think that now is not, the operator is not anymore Pacific, but is, or Frontera is, I think it's Ecopetrol. But this produces a huge amount of water, you know, more than 1 million barrels per day. So it's a huge, it's almost like a water producer. Okay, so this is what the system we developed. So the operator, they take some well tests, and that goes into the database. On top of that, you have some measurements. They didn't have online measurements of water cut, but they had measurements in the lab. So this goes into some database. Part of it was in a software, part of it was kind of Excel files. Then they have a pipe sim model in a network directory. And we use those two in our optimization template that we developed it using a software called Pipeit, which is for this integrated asset modeling. And this is the optimization engineer is interacting with the template, but you have also this production systems engineer who is carefully tuning and updating this model, is also interacting with the PipeSim model. And on top of that, they are in the field, which is far away from Bogota, from the capital. They have a person that they are, you know, depending on the constraints every day, you might have some changes in the power available. You might have some changes in the amount of water that is processed in the facilities. So then he comes and he gives the constraints that they are updated in this template. So it's quite complex. And at that time, I think we didn't have so many good tools to, you know, that like we have today to integrate information and to gather, filter information. But, you know, it was quite effective. So that's the optimization. That's looking more into this part. Okay, and here we were using the PipeSim model, and PipeSim had at that time, and I think they still have a module to do optimization called the Well Optimizer. But at that time, it didn't work because we had a lot of constraints. We had a lot of variables that we wanted to change, and it didn't work very well for this problem. So what we decided was to do optimization using Pipeit, in which we have to run this model several times, and we were controlling that through OpenLink. And then we, for example, we substitute conditions, frequencies, and we have also PSPs, PCPs, and then we calculate a new condition, and then we move there and check. So this is like the optimization engine. Okay, and we have the constraints to fulfill. And at the end, if we accept the solution due to convergence or due to time, you know, the run was quite time consuming, then we report these values. And it's not that they are right away applied in the field, but they are then discussed by the production optimization team, and they are discussed later by the operator, okay, by the field operator. So this is an example. This was, you see the magnitude, the number of wells that are involved. And this was what we were, this particular case, just one case from the ones we studied. So you maximize oil production, then you change the ESP frequencies and the progressive cavity pump rotational speed. Then you have some limits on the frequency that you apply. Maximum water production is limited by the capacity of the battery. And then the suction pressure. And then this is the well liquid flow rate, due something to do with the formation, the stability of the formation. And then this is the limits on the up thrust and down thrust, okay, this minimum and maximum rate. So you see here, like what they were running, the model initially was, you know, in this combination of water and oil. But then after we run the optimization for a few iterations, well, we already find a better point with an increase in oil and a reduction in water. Okay, it was again very modest. Okay, 8%, but it's still kind of an increase. So some comments about this is that it gives you some non-intuitive actions that you wouldn't figure out if you were doing it by, just manually. It gives you some good insights. When these changes were applied to the fields, they gave a similar increase reportedly. Then the one main challenge was how to motivate field operators to adopt the new technology. Sometimes there is a bit of skepticism that how valid are the models and how good they are and how much can we trust them, and on top of that to use the technology, to use this optimization interface. So was some training is needed, some education is needed, and you need to have people also that trust and believes in the solution. Also interesting, so they was trying to flag limiting constraints. What things, if you were going to do some investment in the system, if you're going to do some changes, what can you do to make things better? Again, this is something that can be flagged from the optimizer, and you can say, well, if I increase the production capacity, the water handling capacity, then I will have so much more oil or the power, or you can add new constraints depending on the case you have. The running times were quite extensive. They were from 8 to 24 hours or more. And it became a bit typical to accept so just unconverged solution. You don't wait for the optimizer to tell you that it's finished, it's completed, but you just look at the pool of existing points that you have, that the optimizer has looked at so far, and then you accept some solutions that they are better than the current, but they might not be the best. Okay, this limitation in commercial software is this well optimizer that could have been very useful if we could have used it at that time, but unfortunately we could not. And I think they have improved since then. And also the added value is that simply by quality controlling the model, you have had this, you were able to, if there was a big deviation, maybe the model is poor, but sometimes something is happening in the system that is not included in the model. Okay, like you have, for example, plugging of a pipeline, or you have something strange happening in the formation. So here, just very quickly, one thing that was common and we were trying to address, but we unfortunately were not able to do it very successfully, was that when you increase the frequency in a pump, typically you're going to reduce the bottom hole pressure. And this is going to cause some more coning. So people were concerned that if you had already a behavior of expected water cut versus time, that by doing that, well, you're going to accelerate and you're going to create early coning and you're going to produce early water breakthrough. So we were looking at this issue and just made a bit not completely successful, but we were looking using a reservoir model and history matching our model to the production data, and then trying to predict from there also the bottom hole pressure. So you see here to the right, this is the water production of the model and the data, and it's quite a good match. But when you go to the bottom hole pressure, you see that actually there are some significant differences. And we were speculating all kind of ideas. Could be the aquifer, could be the coning, could be also that you've created an emulsion in the pore, and actually the viscosity is not, the effective viscosity is not the viscosity of the oil, but it's of a mixture. But really, if you have more interest, you can see what we did there. But I think we didn't come to a full conclusion to what happens. So then, after looking at the running time, that was quite significant, and we wanted to run more and more cases. Well, we looked into how can we speed up this optimization. And one of the ideas that came was to use a proxy model. Came from Arnaud Hoffman. He was in Petrostreams. He was working in his master thesis in a similar method. And he proposed to use the method on this case, and actually was quite successful. So the idea is that you take some parts of the system, like in this case, I take this well with this IPR. Okay, and then I run, here is plotting the liquid rate with the frequency at a constant wellhead pressure. Okay, and then I run for different wellhead pressures. And what I create is a collection of points. And then I'm not going to use the model anymore for that part, but I'm going to use the collection of points. And similarly, here you see a flow line. Well, what I do is depending on the water cut that I have here, then I run different rates, and then I record is the delta P of the flow line. And this is not something, brain surgery. This is something that is already done in, for example, some software like from Petroleum Experts, GAP, they represent the wellbore, the tubing, and the IPR with a collection of points. Okay, as far as I understand. But in this case, the main idea was to put everything in terms of a collection of points and solve the collection of points. And what you do is that you interpolate. If you want to know, for example, the value here at 55, for example, you actually didn't run that point, but you can interpolate between these 2 points. Okay, so it becomes, from a nonlinear problem, it becomes a linear problem, or a piecewise linear problem, okay, PWL. So when you do that, then you have to add some more constraints. Well, the pressure at this point should be equal to the pressure at this point, and also, so you enforce some constraints. You have to say that the sum of the rates, these 2 rates should be equal to this rate. Then you have to calculate water costs. You do almost everything manual. You're solving the whole system manually, but you are using this collection of points. The good thing was that the time was significantly reduced. Now the optimization time was very low. Okay, the table generation could be partly automated using this open link, and the deviation was very acceptable. Okay, but this requires expert knowledge if you want to modify the network topology, because you have to change these things, these equations. So if you, for example, now add a new cluster here, then you need to have some knowledge to how to change that. This was implemented using AMPL, which was a programming language that read the tables and performed the optimization. So just to show you the usefulness of this approach, here you have from this one of the papers, all the cases that were run. Okay, you see constrained, not constrained, you have some variation of conditions. But here I'm going to show just the base case, which you have some constraints. And then what happens if the water processing capacity is suddenly halved, okay, so suddenly reduced by half. Okay, and you see here, this shows you each one of these sticks. It shows you each well, okay, with the water cut. And I think the blue one is the base case. So the values that tells you, well, you should operate here to maximize oil production for the base case. And then when the sudden drop in capacity, that could be because one of the processing trains is in maintenance or something happened, okay, it goes to half. Then the orange tells you what you should do to still keep high oil production. Okay, so you see it gives some things that maybe they don't make much sense, okay, to us. Like, for example, I think some of the wells, what we saw, maybe it's not in this case, but we saw some wells with low water cut, they are reduced or they are closed, okay, which might not be something that sounds very sensible to do. But also something interesting, if you see here, even if the reduction in water processing capacity was by half, the reduction in oil capacity was not half, but was 20%, just by this adjustment of the frequencies. Okay, so it tells you that actually it can have some value to use this to advise you how to operate your field. Another thing we did was to look at, well, usually this is the feasible area operating region. Okay, remember, has to be modified by viscosity. But what happens, now, especially in these days, you're very interested about the energy usage. You want to reduce the usage of energy. And that can also give you, maybe you can put more wells and you can put more ESPs. So the intention was, well, what happens if we make it close to this line, which is the best efficiency line? Here is where you have, like, close to it, you get minimum power usage. So what happens if now we try to reduce that area? So what you see here is trying to reduce that area, and we are reducing the margin from 30%, 20, 10. And you see, yes, the power is reduced, but also the oil rate is reduced. So you're losing production by doing that, okay? Which gives you also a hint, if someone that is listening wants to work a bit more on this problem, well, we should look into not only changing, operating closing to the best efficiency line or changing the frequencies, but maybe we can also look into changing the pump model every certain time. Like if you have to replace the pump every 2 years, well, you might look into a different model that allows you to have higher power efficiency. Okay, we didn't look into it, and it's a tough problem. You have a database with a lot of pump models, and you have a lot of areas, and they depend also on the number of stages. And so it's a very challenging problem, but I think there is something, you should do something like that if you want to achieve both oil production and low power. Okay, then something that we were also took with us from this project in Colombia was that well, the models, they are really very uncertain because especially because of this oil water emulsion issue. You have the emulsion of oil in water, and you can have this inversion point, you can have the diluent injection, you can have all kind of things that they can, it might be that our models, they're not, we cannot trust them 100%. So what happens, how that affects our optimum? So yeah, what we did was to say, well, now we're going to assume that each one of these, and this was very easy to make it in terms of a table, because you can multiply each value by a fraction. Okay, in this case, this one shows that the same curve of delta P versus rate, if you say, well, there is an uncertainty, or there is might be an error in the model associated with it of plus minus 20%, that gives you actually a band. It doesn't give you anymore just one unique line. So how much will that affect my results? So what we did is that, well, we had on the tables, we had some base number, okay? And then what we did said, well, it could be that, and this is kind of a typical range for multi-phase flow models that you can have, they can be 20 plus minus 20% accurate. Even a good model with a good simulator, properly tuned, this is a common difference you might have. So what we did said, well, what happens if we had that? Okay, we have a factor F that goes from 0.8 to 1.2. And then what happens if that happens, that if we have that, that difference? Okay, so what we did was using Monte Carlo, and that means we take a sample, a random sample from that range, we multiply our base numbers, and then we run the optimization. And then we read the results. And then we take another number, run the optimization, and take the results. And we repeat that many, many times, and we do that for many, many variables, not only one. So after that, with all the collection of results you have, you perform a frequency analysis and count, well, which one comes up the best, the most. Okay, so these are the results on the oil for one of the cases that we have in our publication, that this is the oil or total field oil rate. And this is how it affects. You see, you have more or less some spread. Okay, not much, but you have from 8,800 to 9,100, and maybe you have some lower values on here. This was using 10,000 optimizations, or 10,000 of these samples, and we were including 17 uncertain variables for each well and flow line. So you might see there, well, my results are going to be dependent somehow of the uncertainty. But what about the frequencies, the optimal frequencies? And what you see is actually that most of the cases, well, the original frequency is still the one that should be used, okay, 40 or 60. And that gives you some trust that even though you cannot trust exactly on the values of oil produced or the suction pressure, it's still, it tells you that the optimum is not that much affected by uncertainties. Okay, of course, one thing that could be missing, if your models are less accurate, okay, less than 20%, maybe there is a big impact. Okay, maybe they become more spread, this chart. But for this case that we analyzed, actually it doesn't have that much impact. You can maybe run this, you can maybe assume 40, okay, and this could be good for most cases. Yes, so this I'm going to like the last part of the presentation is some applications on offshore oil fields where I have no network. And again, the same case, heavy oil, strong aquifer with water injection. And here we try to apply the same method, and now not using really for the optimization pipe sim, but using this piecewise linear method. So this is one case, and here we didn't have collaboration with Equinor, who is the operator of the field, but actually we wanted to show, that it could be used, and we use data from, whatever we could get our hands on the open domain. And Øystein, he worked on that, trying to develop. These are so they are platform wells. So here you have the tower, and then you are able to replace ESPs when you need that are here, and all of the wells are very close to the separator, and you have these two platforms, and you have injection wells, and you have also production wells. And this is a typical profile. Here you have, I think oil is the green one, the total liquid is this violet, and then the water is increasing, okay, dramatically with time. So Øystein, he applied the same method, and it found some also interesting results. There is this publication if you want to check it. And here, even though they had diluent, we didn't consider the effect of diluent. So we didn't optimize considering diluent injection. Then another case I worked with is on a heavy offshore oil field. If you read the paper, you might find out, what field it is. But here the main target was that you have wells that had, again, was platform wells that they have ESP and they have diluent injection. But here the main focus was on the diluent. How much of diluent should I inject per well to meet some target? So the system, I tried to make a sketch here of, how it looks like. I think you had 2 reservoirs. You had wells in each reservoir, and you had, for each time, you had some target that was generated using from the reservoir team. Okay, they came with some targets in time that you had to honor, that they wanted to produce. And then you are injecting diluent. The diluent comes from a common source and is limited, so you have to be smart. How do you allocate diluent in each well? And then you also have some injection in the processing facility, because when you cannot help anymore the lifting, then you can also help the separation, and then you can also meet the export and some technical specs regarding viscosity. So what we were looking at, and here there were many constraints. So you had the amount liquid rates and oil rates and water rates, they had to be below some limit. The diluent was limited. And then you had the wellhead pressure, also you had to be above certain number. The processing facility, you had the processing capacity of oil, gas, of oil and water. And also if you have the formation of emulsion, then it will be much difficult to separate. So there was some constraints in the viscosity. And yes, and also on the export, you had some additional constraints. So these are some results I took from the paper. So you see here is this is time, and this is incremental oil production. This is the cumulative oil production, and this is with respect to the case with no diluent injection. So initially the plan was to inject with a fixed percent, okay, 5% for reservoir and 10% for another reservoir. But then by doing the optimization in every time step, well, actually you see that you are able to produce much more oil. Okay, 3 million, so it's like 1 million difference in between, maybe less 0.8. Okay, and this is how the demand looks like of diluent when you do with a fixed percentage or when you use the optimization. Okay, the optimization is the red one. So you see it's significantly less than the other. And especially at later times when the system becomes water dominated, when the water continues, the effect of the crude viscosity is not that important, then you don't need to inject any more diluent. Okay, so I think this like shows a bit, what, and this was used. This field was not, I don't think at that time was in the planning phase, and they were planning how much, what kind of how much to inject every year. And one thing that was also important was that we could provide feedback on what rates you should produce, if these rates were feasible or not, because it could happen that the rates that were calculated or they were estimated by the reservoir management team, they might not be able to produce because all kind of constraints that you had in the system. Okay, so I think that's all. I think I, finish early, I think. So, but that's all I had to prepare for today. So I have to say that model-based production optimization can help in operations and also in the field design phase of ESP boosting systems. We kind of try different cases, and we are confident that it provides some value. Especially when you have networks, it's challenging because of the dependency of what you have in the system of the different wells. And if you change conditions in one well, the frequency is going to affect also the conditions on another well. So it becomes challenging to balance up that situation. And for that, optimization actually can help you quite a lot. The proxy models based on piecewise linear models have a lot of advantages. Okay, they allow you to run quick, they allow you to find accurate, and they allow you to do a lot of cases, to do, for example, do sampling, to consider uncertainty, and to change a lot the constraints, but they are challenging to maintain. Okay, you need to have an expert in the field that knows how it works and knows how to change it. And if you have any change in your system, because there are always going to be changes. Either that the system is going to change, you're going to add new wells, or something might happen with you might redirect to another battery, or you might have some change in the power. So you need an expert, a person that is able to make those changes. Okay, and also to update the tables when you have when you have changes. And in our case, that was something very nice, is that sometimes model uncertainties, they have limited impact on the optimal settings. Okay, so you sometimes don't be skeptical or be, pessimistic that this won't have any value, because, the models, they are good for nothing. But actually, even the model is a bit good for nothing, you can still get useful inputs from the model, okay? Because you can see that the uncertainty actually doesn't change that much. Not the optimal values, still you might have a significant change in rate of oil, for example, but on the optimal settings, okay, on the diluent injection, and on, for example, the frequency. Yeah, and that's it. So I just have to say there are also many things that are interesting to look at. We haven't looked yet into the combined problem, okay, frequency and diluent injection, because simply was not the cases that we looked into. They had different priorities. One was on frequency, one was on diluent injection. And also that one thing that I believe is worthwhile looking into, but it's a very tough problem, is to look into replacing the ESP type model number of stages, to allow that to be also a factor. And that's not something that you can change at what point in time, but maybe you have to schedule the replacement in 2 years, 6 months, or depending on 5 years. But maybe there will be also more potential for improvement besides diluent and frequency. And here I add some, if you have any questions, thank you to everyone that I was working with during these last years, because also we publish these papers, and then we put a lot of data there that, some people can check what we have done and also can use it to take it further. And also I have put here some references of the figures and of our papers that, if you want to check them out more closely, that's, you can do it. But again, thank you for the invite. I don't have much contact. I knew you existed, your university, but, I thank you for inviting me. It's a pleasure. And yes, if you have any questions that we can answer in this time, that would be fun.
Thank you so much, Dr. Milan Stanko, for the presentation. It was really fruitful. So if anyone have a question, he can unmute himself and ask directly, or he can write it on the chat and they can ask instead of him. So I have a question regarding the optimization. So you have used piecewise linear regression. These algorithms take into consideration only one variable at a time. So which algorithm have you used in order to optimize the problem?
Not really one variable. So it's simply that, for example, you have this nonlinear function here. We can take. Okay, so this nonlinear function. So if you're going to run it in PipeSim, or you were going to use a nonlinear equation, you have to approximate this as, for example, a polynomial, okay, a second order polynomial. Yeah. What we do is that we put breakpoints. So we, for example, point one point here, one at 25,000, one at 50,000, 75, and 100,000, for example. And then if you have a rate which falls in between, well, you interpolate on that.
Yes.
Okay, so but you can use really any. For the pump, for example, you can then change the frequency. It becomes a variable. But to find the value of liquid rate at that frequency and at that pressure, you have to do linear interpolation between those 2 points. So that's done with a technique. What we use is a technique called SOS2, a special order set 2, in which what you do is that you assign a variable to each one of the points. And then, for example, if you want to model a value which is in between these two, all the other values associated with all the other points are going to be 0. And the values associated with these 2 points, let's say you're exactly in half, one will be 0.5 and the other will be 0.5.
Yeah.
Okay, but this makes it into a linear problem. And when you have a linear problem, it makes it like it's usually much easier to solve because you have a lot of methods which they're going to find the global optima. It's not that they are going to get bogged down by one local solution, or you're able to usually ensure some sort of global optimality, that the solution you found is actually the best solution from all possible solutions. And it's usually much faster.
So what is the difference between using the piecewise linear algorithm and using, for example, neural network as a regression parameter?
So I think the neural network, you have to train it. So
Yeah.
you have to, you provide it with some data and it's going to train it, and you're not sure what it's doing for the points where it doesn't have data. Okay, it might be that the approximation it makes is good, or it might be that the approximation is bad. In this one, you're not actually, you don't need to train anything, because what it's doing for the points that it doesn't have, it simply interpolates. For the conditions that it doesn't have, it simply interpolates. So for example, if we were testing something outside of 70, well, it's simply not going to give you anything because it doesn't extrapolate. It simply has to be within the original bounds. And each one of the points here is coming from the model, so you have a high trust on the numbers, because they come from PipeSim. This comes from some physical simulator that someone ran and gave you that point. Okay, while in neural networks, you're not sure the numbers that you're getting, if part of it might be the points that you use to train your network, but part of it might be simply the approximation that the network is doing.
And was the optimization stochastics or gradient based?
Yeah, this is not stochastic, and this one was gradient based, the one we did for Rubiales. Here, when you do this optimizer required, because to find the directions where to go next, okay, to maximize oil production, it's like you have to do perturbations on the system. Let's say you want to change the frequency in well 1. Okay, so then you have to, the frequency is initially 60, then you do a small perturbation, you do, for example, 61, and then you find that derivative, you find that partial derivative, and then you assemble your whole matrix of derivatives with all the frequencies. You do the same for all wells, and then that's how you find your next point. Okay, you choose the direction in which you're going to get maximum oil. Okay, maybe some frequencies have more effect than others. While for this one, you use, I think what we use is, you can use linear methods that they don't depend on gradients. So I think this was, we were using Cplex, and I think this uses, for the integer part, is using branch and bound, and I think it's using the simplex model for the continuous variables.
So, but if you take like into consideration both the diluent and the frequency, you cannot really get the optimum, because you are going to get into many dimensions, and at that dimensions you are going to need the stochastic approach more than gradient one or linear one.
Yeah, stochastic you typically use for when you have some uncertain parameters that you want to find out the optimal considering the uncertain parameters. We didn't use that approach here, but we simply use it with sampling. So we use this approach that we just assume that the input is, or the model is uncertain, and then we use sampling. And because this runs in 7 seconds, you can really do 10,000 iterations very quickly, okay, in less than 2 hours. But so stochastic, we really didn't use it here, and maybe it's interesting to use it. I think definitively including both variables, the frequency and the diluent injection, is going to be more challenging. But if the problem runs and it can be solved, for sure, this method will find a solution. Okay, the piecewise linear. The only thing is, if the size of the problem becomes too big, then it will take a long time to find a solution, and it's going to be impractical for application in the field.
Yeah, I think that using both the diluent and the ESP frequency and then generating the result using the model. So we can use that data. We generate different models. Once we generate different models, we can train like a neural network to take care of that domain, and then we can do the stochastic optimization. When we do the stochastic optimization, it can solve it in a few seconds. I would say 20 to 30 seconds, and it can give you the global optimum for both values, taking into consideration the model data that was used to train the neural network.
Yeah, we haven't tried maybe something interesting
Yeah.
to look into. As I mentioned this, we haven't done much work on this since maybe 2 years, 3 years ago. So, but with all kind of new tools and new methods that come lately, it could be worthwhile to revisit using something different. At least what we found for our problems that we had, that really the champion is piecewise linear, although it's difficult to implement and it's a bit cumbersome, but it's it is what gave the best result.
Yeah, it gives better value. Yeah.
I have another question, Dr. Milan. One of the main challenges in the multi-phase flow is choosing the model, because you mentioned that even if we choose like a fit model and a well-calibrated model, we will have at least 20% of uncertainty. Which model have you used, and how did you make sure that it's the best one that fits your problem here?
Yeah, that's a difficult question. So the model was calibrated. I don't remember, it was a bit long time ago, but the model had been, in the case of Rubiales, had been calibrated with data from the field. I think they were using some model considering slip between the phases. I don't remember which one. I think it was maybe one of the classical. And I think, if I remember correctly, we were using an emulsion model called the Richardson emulsion model. And this was calibrated using data from the lab. But so I think considering slip and some emulsion viscosity, considering the kind of the concentration of the dilute phase. I think this typically assumes that these are exponentials. Where is it? Yeah, this one are exponential. You have two exponential equations, one for this side, one for this side.
Okay, something else you've mentioned in the first of the presentation, that you did not take the interaction between the reservoir and the wellbore like thoroughly. Which model did you use in the interaction between them? Is it a simple one like the Vogel, or?
No, this production, at least in this case, Rubiales was undersaturated, so we were using just a linear PI, but the PI was changing with time, the PI and the water cut. Because from well test, you could get now the new PI, liquid PI, and you could get the new water cut, and then we substitute that into the model. And the other one, on the offshore field, we have used. I think these numbers, we didn't model the inflow because those numbers came from reservoir simulator. So the reservoir simulator provided the rate and the bottom hole pressure. So you don't have to simulate that part, but just from that part and that point up.
Yeah.
Sure. Okay. Thank you.
So does anyone have questions?
Yeah, I can say something here. Hello, Milan. This is Amin. I'm
Hello, nice
currently
to see you.
working. Yeah, same to you. Currently working on Mariner in the UK. It's a heavy oil field and viscous oil. Not really a question, but just to thank you for the presentation. It was very relevant and yeah, very fruitful actually. And yeah, I learned a lot from it. So thanks for all the good work.
Yeah, thank you for your comments. Yeah, I mean, he was my student a few years back. So, but now he's has been some years in the industry. But I'm happy that you're working on that on Mariner. Okay.
So if you don't have any questions, we would conclude. So thank you so much, Dr. Milan, for the presentation. It was very fruitful. And thank you for putting your courses online and all the information and the knowledge shared for publicly to the people. It was very useful for a lot of people. It will make a lot of impact on the petroleum production. So thank you so much for your time today and for the fruitful information that you shared. So I will send you the recording of this session, and if you may approve it, you can put it on your YouTube channel. So thank you so much.
Okay, thanks again for inviting me, and good luck. Yeah, you now have still a long day to go in the US. We are still now, I'm going to have dinner soon. So
yeah, enjoy your
so
dinner.
yeah, but take care. Thank you to everyone who attended. I don't know, I think we have a few.
Yeah, we
Sure
have
if I recognize.
Thank you.
participants. Yeah.
Okay, take care.
Thank you.
So,
Bye-bye. Have a good
yes.
day.
Thank you. Goodbye.
Bye-bye. Stay safe.